in order to better understand normal random variables, we're going to need to do some quick revision of binomial random variables. Now, when do binomial random variables crop up? It's when we have a finite number of experiments, or trials, we might call them, a finite number, each with a certain probability of success or failure. So let me give you some examples. Really simple example is rolling dice. If I roll a die 20 times, how many 5s do I get? That's an example of a binomial random variable. Another simple one, if I flip a coin, say 10 times, and I ask how many heads? Now those are two quite neat and tidy examples. Let's apply this to the real world. Another example might be, if I sit in my windowsill and wait until I see 100 bees, how many of those bees will have 2 stripes? Say 2 stripes. I had to Google roughly how many stripes a bee has. That's an extra thing for you to do. Another one is in a sample of, say, 50 people who are tested for a certain illness, how many of those people have the illness? The illness. In order for these to be proper binomial random variables, we need to make 2 assumptions. Those are that each one of the trials are independent of each other and that the probability of success is constant. So, for example, the dice, if I roll a 5, that doesn't have any impact on whether the other rolls are 5s, and that the probability of success is always a 6th if we assume it's going to be a 6th. That is nice and tidy for these ones. Those assumptions might not necessarily hold true when we apply it in real life. You could imagine that if I spot one bee, then the next bee might be more likely to have 2 stripes because they might be brother and sister. Let's attach some notation to this. If f was my random variable for number of 5s, I would say that f twiddles, that weird symbol there, b, the first number that I put in this thing that says that it's a binomial distribution is the number 20. That's the maximum number of successes, and then the probability is, in this case, a 6th. For the coins, I would say, let's say number of heads is the random variable h. It's binomial. Maximum number is 10, and the probability we're going to assume is a half. For the real world examples, we often actually do things the other way round. We might say that the number of people ill is a random variable binomial with 50, but we don't necessarily know what p is, and we do some experiments to try and find out what p is. That was the whole point of the binomial hypothesis testing that we did last year. Similarly, for the bees, number with 2 stripes, that's binomial 100, and we might do some testing to find out what p is as well. Let's think a little bit more about the simplest example here, the coin flips. Imagine actually flipping a coin 10 times and counting how many heads we see. So intuitively, the most likely outcome seems to be 5, because we'd expect to see a head half of the time. Away from that, it seems very unlikely that we'd see 10 heads in a row, or 0 heads in a row, because that implies 10 tails in a row as well. They seem very unlikely. But what about numbers in between that? What is the exact probability, in this case, of seeing exactly 6 heads in that run of 10? We can calculate that probability using what we know about the binomial distribution. I have here a histogram that's been plotted of exactly what we've just been talking about. And this has calculated the probability of seeing exactly 6 heads. I can do that like this. Exactly 6 heads as 0.2051. Now you could look back in your notes and figure out exactly how that number is calculated, but for now we're just going to rely on the calculators to say that that's 0.2015. The histogram shows intuitively what we understand about it, that it's very unlikely to be up here or down here, and it's most likely to be 5. I'll put a link to this GeoGebra file on in the description so that you can have a play with it yourself. I'm just going to look at one more example, that is the dice roll example. So in that case, n was 20 and p was a sixth, so I'm going to round that to 0.1686 and press enter. And that's what the graph looks like for the dice roll and the probability of getting certain numbers of 5s. So it looks here like the most likely outcome is 3 5s in 20. That makes sense because that is roughly 1/6 of 20. I want to get you doing the maths now. I have for you, for that binomial random variable we were just talking about, our number of 5s in 20 on the die, can you use either the GeoGebra app that I was just talking about, or try and remember how to use your ClassWiz to figure out these probabilities? So the probability that f is 3, that f is 2, that f is less than or equal to 2, and the probability that f is between or including 5 and 7. Pause the video now and see if you can figure that out. Pause. Play. Hopefully you've had a go at those and got these numbers. If you've used your ClassWiz, you will have remembered that to get these ones, we've used the binomial PD setting, that's point distribution, and for this one, we've used the CD setting, which is cumulative distribution, like cumulative frequency diagrams at GCSE, like adding up along the way. This one here is slightly harder to get. It's very easy to get if you've used the GeoGebra app because we can just plug both numbers in. But on your ClassWiz, you hopefully remembered to do, well, we need the probability up to 7 and including 7. But we're taking away all of this up to 4. We still need to include 5, so we can't take away up to 5, but we need to take away the probability of f is less than or equal to 4. And that's how you figure it out on a calculator, by finding those two values and taking it away. If you didn't get these values and feel like you need a bit more practice, just go back to your Year 12 textbook and there'll be a good exercise in there in order to practice finding these binomial probabilities. So let's move on now. We're going to go back to this lovely app here. Tell you what, I'll change it back to our coin flips, so it was n equals 10 and p equals 0.5. I said in the last video that binomial random variables are examples of discrete random variables. They can only take particular values. So this one can only take the integers between 0 and 10 inclusive. The normal distribution, however, normal random variables, are continuous random variables. They could take values, any values, between these integers here. The shape of a normal distribution, if we were to put it on a graph, is very, very closely related to a binomial distribution. We'll see why in a later video. But for now, let me just click on this button here and change this so it is a normal distribution. And we can see how that shape is very similar. In the upcoming videos, we will have a look at exactly what this graph means.